My name is Pat Grady. I'm a solution engineer at AdSwerve, and I'll be walking you through the foundations of digital marketing. Let's go ahead and get started. Welcome to today's episode 2 of our series on advanced analytics for digital marketers. And today we're going to be looking at embeddings and semantic search. And these are sort of the underpinnings of what we're seeing today in technologies like ChatGPT or Google's Gemini models, large language models. And we're going to be going back to the fundamentals and looking at the mathematics that lead to these new capabilities, and then look all the way through it and work to the point where we're actually implementing semantic search algorithms against a corpus of data. And then in the part 2 video of this series, after sort of the lecture, demonstrations and learning, then we're going to actually implement semantic search appliance given some data and that has a search engine experience and a conversational agent. So let's go ahead and get started with the actual sort of content. If you're above the age of 40 like me, then you'll probably remember texting folks required working a 12-digit keypad across a 26-character alphabet space. And so we actually, to say words like hello, we actually had to type 4 twice to get the H from the middle, 3 twice to get the E. Then we would have to hit 555, wait a little bit, hit 555 again, hit 666 to get the O, and then after 13 key presses and an awkward pause, we were able to actually get to the word hello. Then someone came around and said, oh hey, maybe if we create a dictionary of words and their corresponding numbers, then maybe we can shorten that experience, and instead of entering 13 values for a 5-letter word, maybe we can go and enter 5 values for a 5-letter word. And that worked great until it got to the point where there were words that had multiple responses, and if you type 43556 in this scenario, you're either going to spell hello or gecko. This led to the idea of, well, maybe we can look at the probabilities of different words and make a determination. If someone is beginning a sentence, maybe they're not beginning the sentence with the word gecko, but rather the most likely word would be something like hello. Or if they've gone and been describing lizards, or hey, I bought a new, and then they typed 43556, then gecko would be what shows up as opposed to hello, since you would never say hello, I bought a new hello. And so this is just an example of how you sort of start to think about probabilities in the relationships that words have to each other in a probability space. And you can think of this, if you're above the age of 35, maybe you've actually played this game on the product formerly known as Twitter, and there were these predictive text games. So you would say, like, how about we use predictive text to write your own epitaph? So you type out, here lies Pat, he was, and then you just start selecting the sort of predictive text on your iPhone to basically flush out a grammatically correct sentence, because it's using probabilities and relationships of words. As you start to construct that sentence probabilistically, this grammatically correct and syntactically correct and even semantically correct sentence appears, even if it's been hallucinated out of thin air, which is sort of the underpinnings of one of the challenges that we face with large language models today, is this concept of hallucination. It's because large language models fundamentally are just constructed using probabilities of words and relationships to each other, and there's not much guidance or guardrails as to what's true or not true, especially when there's sort of these vague probabilities that exist between certain words. So let's actually look at the underpinning modeling that, circa 2013, when folks at Google published the efficient estimation of word representations in vector space, which we now lovingly refer to simply as embeddings. This was really cutting edge breakthrough stuff when they were introducing concepts of modeling like the skipgram. This fundamentally is one of the models that is really used at the core of any kind of semantic search appliance. You take a corpus of data, and to train those probabilities, you basically create windows across that corpus. In this example, we have one sentence out of potentially millions or billions of sentences that we could use in a training corpus, and we've windowed out and selected a word, looked forward and backwards by 2 words in this particular case, and then 3 words in this particular case, and really defining a labeled data set of the keyword. And then once we have these skipgram corpuses, then we're able to calculate all the probabilities of any given word, and then now have a model that, when given a word, is able to sort of construct this probability map of using words that came prior and words that come after from the training corpus to basically say, like, okay, this is the word that you probably want to put next or before that given input word. And fundamentally, when you think about it, when you give a prompt to a large language model, you can sort of envision that prompt is sort of interpreting your sentence, mapping that semantically to the corpus, and then identifying the intent, identifying what you're wanting, and then reconstructing that in a sort of coherent response. Now, let's dive in a little bit and look at what happens when you encode words into a highly dimensional space using these vector embeddings and just simply map those out in a 3D space. So in this, we sort of have this, you can have a male-female kind of relationship that exists between different words. So if you start with king as the one version of the word, then the male-female relationship would be queen as the other word, sort of verb tense. Walking turns into walked. And then if you're looking at the country capital representation, things like Ankara or Turkey would then turn into Ankara, et cetera, et cetera. So those types of relationships we're able to sort of visualize in this space. And so when we look at something like the word2vec 10K sample set, we can sort of reconstruct this. And so here we're viewing lots and lots of different words, like for example, silver. We can click into just any of these words. Let's click into the word bat. And then we start to get all the different sort of words that are associated with that in that three-dimensional space. Now, if we sort of exclude that example and just use one of those examples that we were just looking at, we can definitely see, and let's just plot this in a two-dimensional graph, we can definitely see that king and queen are somewhat associated or near each other. And then if we were to add something like less related, like a table, we find that to be something that shows up way over on the other side of that 3D, or that's in this case a 2D vector space. So king and queen are much more similar to each other than table. And so the probabilities of table and queen being in the same sentence are just simply lower than the probabilities of king and queen and king being not necessarily in the same sentence, maybe in the same paragraph, or maybe in the same intent of the conversation. So that's kind of interesting. But what happens when we actually have data that looks like this? Images. In this case, these are images of hand-drawn digits. And this is a common corpus of data that's used to sort of benchmark machine learning models. And the idea is that you use a training corpus like this and be able to predict which digit was written. You can see like a bank being really interested in this kind of technology for scanning checks. So this has just been around a long time. So let's look at these images from that sort of vector embedding space. And so to go from those data set or corpus of images to something like this, which is able to organize those images just by analyzing the pixel densities. Now, how did it do that? Well, it was able to take each image and break it down pixel by pixel and basically create a vector space that represents color or intensity or contrast in this new matrix of values, the embedding. And then when it sort of plots those embeddings out and compares that and classifies them and reduces the dimensionality of that highly dimensional space, then it's able to sort of plot those similarities to each other. And so some of the things that you get out of this type of analysis is you see things that are very similar to each other. So the 7, 9, and 4 are all grouped together in this very close embedding space, whereas something like 0 is highly differentiated, stands off on its own. 1 is highly differentiated, for the most part stands off on its own. But then things like the 3 and the 5 and the 8, again, same type of concept. 3 is just half of an 8. 5 is just missing the line that connects the two between. So you can use this type of analysis or envision that this type of analysis is able to find similarities. So be it pictures of numbers, maybe it's pictures of items within a store, an e-commerce store that you are operating. So in that kind of concept, slightly more complicated pixel space that we're analyzing here. And we can still do the same exact thing where we just convert those images into vectors, reduce the dimensionality of those vectors to something like a 2D or 3D representation, and then plot those vectors in the projector space. And we can sort of see the relationships between these and understand that, okay, sneakers, sandals, and ankle boots actually have a lot of similarity to them. Just from a pure image pixel analysis, it's able to identify that these things are related. And we don't have any sort of label when we're doing that classification. These images are similar to each other with labels or without labels. Just like sort of dresses and shirts can be sort of confused, and there's almost no way to distinguish coats from pullovers in this particular example. And then of course bags are sitting way off here on their own in their own little space. So when we take that kind of concept and to a more production ready environment, you can envision a store and they have thousands of products, and anywhere from hats and apparel to dresses and blouses to just regular shirts and shoes, and when we plot those images in the relationship of those images to each other, we're able to build out these more complicated embedding spaces, which then leads us closer and closer to this concept of semantic search. So when we're thinking about taking these sort of embeddings and then actually turning that into a search appliance, then we're able to make sure that whenever we search for dresses, that we find dresses, that when we search for things like paintings, then we find paintings. And that is something that's critically important and something that we're going to look at in more detail in the next video. So stay tuned, and we'll be running through some actual code and then actually jumping into the platforms to build out these appliances without code and just using fully managed services in the form of Google Cloud Vertex Search and Conversation. Okay, thanks very much.